When you think about data, what is it that you think of? You think of a collection of points, a geometric set of points. Let's get a little more specific. One type of geometric data set is called a point cloud. A point cloud consists of a collection of points, finite collection of points, let's call it X, consisting of points xi, that reside in a Euclidean space. These are all points in some Rn. Maybe that n is really big, who knows? But the points definitely have coordinates. Take a collection of them, that's a point cloud. That's cool, that's great, we're going to work with them a lot, but there's something more general. That is a finite metric space that consists of, again, a collection of points x, xi, but outfitted with a metric, with a way of declaring what the distances between the points are without actually saying where the points reside. Fine print, this metric has to satisfy the definition of a metric so that X is a metric space. Please review your definitions accordingly. Okay, what are these things for real? Point clouds you see all the time when you're looking at vectorized data. Let's say something that's coming off of a 3D scanner. You look at medical imaging data where you've got scans. Yeah, all those points are in Euclidean three-dimensional space. They all have coordinates. Astrophysical data, all those stars, all those galaxies, again, 3D coordinates, explicit points, point cloud data. Robots? Self-driving cars? Oh yeah, point cloud data everywhere. They're using LiDAR. Sensor networks, where you've got GPS enabled? Yep, keeping track of coordinates, good point cloud data. Now, finite metric spaces are maybe a little less familiar, but they're not at all less important. Often, finite metric spaces are encoded in terms of dissimilarity matrices. Collection of points and a matrix that says how dissimilar two points are from each other. That's like a proxy for a distance. What is that? Where would you need that? Oh, consider genetic sequences, where we can say how dissimilar two sequences are without actually putting those sequences in a Euclidean space with explicit coordinates. You could do the same thing with text, with image, with video, where sometimes you might want to embed them in a Euclidean space, but sometimes you just need to keep track of the distances between elements. Similar thing happens with social networks, where the people are like points in a space, and then the distance between two people is how close are they in the social network? How many hops does it take to get from one person to another in the social network? Similar thing happens again with sensor networks, but where you don't have GPS and explicit coordinates, but rather just some notion of proximity, maybe based on rough signal strength, something like that. So whether you're talking about point clouds, whether you're talking about finite metric spaces, these types of data sets are all around us, and they all lead to the question, the big question that topological data analysis begins with. That question is, what shape is that? Here's a data set. Here's a bunch of points. It's just a bunch of points. What is its shape or its form? Now, this is not so easy to answer. There are many different shapes that are roughly equivalent in some form or fashion. It's not so easy to solve. So what do we do? Well, you kind of know how to solve this problem because you have a highly trained visual cortex that is used to distinguishing things that look different but really carry the same meaning or have the same content. But how do you do it? And how do we do it when that data is not fitted to your visual cortex, when it's not in 2D or even 3D? Well, to answer that question, you need more math. You need to ascend and grow some new mathematical skills. We need to learn a lot more to be able to answer this fundamental question in topological data analysis. So let's get going. Given a finite metric space, or a point cloud, what shape is it? There's one construct that has been alluded to previously in this chapter. Consider the definition of a Vietoris-Rips complex. The Vietoris-Rips complex of a finite metric space, X, at threshold epsilon, or epsilon is positive, is the complex whose simplices consist of the following. They are subsets of X such that for all the elements in that subset, the distances are below epsilon. That is, simplices consist of points which are pairwise epsilon close. Let's think about that. You've got your finite set X, and those points, those are the vertices of the Vietoris-Rips complex. What we do is we look at all the pairs of points whose distances are less than epsilon, and we connect them with edges. This gives you the one skeleton. Now, for the two simplices, for the higher dimensional simplices, we need to look at collections of points that are all within that pairwise distance epsilon. That means we're filling in every possible triangle. We're filling in every possible tetrahedron. We're looking at, in effect, the maximal simplicial complex given that one skeleton defined by the threshold epsilon. Okay, that's your Vietoris-Rips complex, but there's more than one way to build a complex from a collection of data points. Here's a new definition: the Cech complex. The Cech complex of a finite set X that lies within a potentially larger metric space M at threshold epsilon bigger than 0, just like before, is the simplicial complex whose simplices consist of the following. A subset sigma of X is a simplex if there exists some point Y in the larger metric space M, so that all the distances of the points in sigma to Y are below that threshold epsilon. So to repeat, simplices consist of points which have mutually intersecting epsilon radius neighborhoods. Now what is this? Well, just like before, we're going to start off with the collection of points. These are the vertices of the Cech complex. Fix your threshold epsilon and look at the epsilon radius balls about these points. If two such balls intersect, boom, you got an edge between those vertices. If three balls intersect, then you have a two-simplex between those three vertices. Continue inductively. That's how the Cech complex is formed. And it seems like a pretty good way to approximate the topology of what you get by growing balls about these points with a simplicial complex. That's kind of interesting. Leads to a lot of questions and a little bit of work. You should start off by verifying that both the Vietoris-Rips and the Cech complexes are in fact simplicial complexes. You could do that. A more difficult, open-ended exercise is to detail the relationships between the Vietoris-Rips and the Cech complexes. As functions of this threshold size, when is one a subcomplex of another? That's not so easy, but it is going to be useful to us later. For now, there's some pretty serious questions that these constructions raise. We've seen Cech, we've seen Vietoris-Rips. Which of these types of complexes is a better approximation of the underlying ground truth behind point cloud or finite metric data? Well, it kind of depends. I mean, they're not the same complex. It depends on the epsilon. It depends on a whole bunch of things. One thing to note is that the Vietoris-Rips complex is a lot easier to compute and to store, since you only need pairwise data between points. That means if you know it's one skeleton, you know the entire Vietoris-Rips complex. The Cech complex? Oh, not so much. You have to check for the intersection of all of those balls, and it's not so easy to figure out, and it's not so cheap to store. On the other hand, if you're looking for the best approximation, if you've got a collection of points and it's on a sphere, and you want to be able to say, yeah, that's a sphere, well, neither complex is guaranteed to give you exactly the right answer. It depends on a bunch of things. So which is it? What do we use? Which epsilon do we use? So many big questions. But for now, we need to move along and take on a deeper, more pressing issue, that being thresholds, which appear both in the Vietoris-Rips and the Cech complex definitions. Thresholds are a perennial problem in all of data science. You've got some experimental data, you need to connect data points. What's the right threshold? Where do we set the cutoff for significance? Whether we're talking about distance, whether we're talking about correlation, Maybe we're talking about similarity, dissimilarity. Maybe we're talking about cost. Whatever the experimental data that we're working with, at some point, you need to set a cutoff and say when things are connected or not. Is this easy? No, it's not easy. If you go too low, then nothing is connected to anything. That's terrible. You've just got this disconnected set of points. That's not what our shape really is. Okay, well, let's turn the dial all the way up. If we go too high, everything's connected to everything. And your Vietoris-Rips, your Cech complex, whatever you got, it's just one giant big simplex. That's not useful either. So, all we got to do is find the perfect threshold. What's the magic formula for getting the perfect epsilon so that when we connect at that level, it really captures the truth? Well then, here's what topology has to say. The best choice is no choice. It's everything. Take everything, take it all, and let the math sort it out. What we're going to do is not choose a particular epsilon. We're going to use filtrations. We're going to take sequences of increasing complexes, add all possible values of epsilon, and work with those. Now recall from an earlier section when we talked about filtrations, nested sequences of subcomplexes? Yeah, time to bring that back and talk about the Vietoris-Rips filtration or the Cech filtration. These filtrations arising from choosing a discrete sequence of increasing thresholds. One shows that the Vietoris-Rips complexes get bigger and bigger and bigger, that the Cech complexes get bigger and bigger and bigger as you increase the epsilons. And here is the last word. The filtration, the whole sequence, contains much more information than any single step, than any single choice of threshold. The perfect epsilon, which may or may not exist, doesn't hold a candle to working with the entire sequence. What is this? What does this mean? Explain, please. Well, we can't, because we're out of time and space in this chapter to fully elucidate this core idea in topological data analysis, that it's filtrations that really capture the shape of a data set. There is so much more that we have to do to be able to explain that statement, to show how that works in practice. There's much more for us to learn together. I am very much looking forward to it.